Well, now we will just create a transmission model, acoustic transmission model, with our simple plate 2 mm steel. I will call this transmission of 2 mm plate. This transition will be computed from analytical calculation. Okay, now for started with geometry, to get a nice view, we just go to 3D geometry, and from this I will go to File and import in the 3D geometry window the Nastran input file that contains material properties, section, and geometry. And here I have to import it in SI unit, so if you're working in ton per millimeter, just put 1000 here and 1 E-3 here, ton and millimeter. And then I need to load the file first. This is this one. And when it is loaded, I just click OK, requesting everything is in the file. Import. You see there is one P-comp that have been detected, that's on, and one material. And then there is the 3 available tab, geometry tab, that displays the PID in the 3D geometry, the shape that add information to the PID, and after the ASEA element, they contained the shape transformed into an ASEA subsystem. So we need to first create the shape, click on the plate, then click here, and automatically the section is allocated to the shape. And then I accept the data, click OK, and from that I have a shape I can edit from here that contain the information required to create a subsystem. So now I create a subsystem from the shape, and I just add a non-resonant pass-through in order to take into account the mass law transmission, the non-resonant transmission in our transmission model. And then I simply send the ASEA subsystem to C+ page model. I deactivate the element, and then this is our plate. Okay, 2 mm steel. And then from this, first, I think I should set up my preference in subsystem setting, especially for cavity. I want always same kind of cavity, and I want cavity at startup by 600 and 120 meter perimeter, in order to, and the color I will put some better color, blue, light blue, like this. And then now I can just create, the normal is oriented along Z plus for this plate. So on the top I will have the emitter cavity. Automatically my cavity is generated with appropriate geometry. I click OK, and then I can duplicate it. Put it here and change name to call it receiver cavity. Then I just have to connect cavity and plate. Or here I will connect on the Z plus face, while the default when connecting is Z minus. In our cases, we don't really care. It's only when you have trim that you have to take care of the face of the surface of the array you are connecting. Then I just put a bit of order in the network, the Z direction. I align everything, okay. And I will add power as constraint. So add source, user, energy constraint. Okay, unit pressure in the emitter cavity. Connect source. Receiver. I don't change really this. I need to put emitter. Okay. All right, this is done. I will probably change also the coupling loss factor color. So for this, I just select both Control W and change color here. And I put light blue like the same color than the cavity. Okay. Now I have a transmission model I can solve. Control R to solve. And then I can get a look to the drop of pressure between the two cavities. Okay, 94 dB on the emitter. And on the receiver, a drop of pressure. And now, if I want directly a transmission loss coefficient, I just here select the emitter cavity, then the receiver one. So the transmission loss tool detects the surface area between them, and then I just compute TL, and it plots the result directly as a TL. Control G. Okay, so I let this TL on the side in order we can use it for comparing with RRI. Now, RRI have been computed in another project, so don't mind, just open this project and then I copy the RRI object and go to the previous project and paste it in the right section. Miscellaneous, sigma radiation from data. When I double click on the RRI object, then as I explained, I need a wave number as well. So I need to go back to my model here and the window here. And then I will graph the wave number of the structure. And plot it here and then send the result in the database. Save. So now, if I go back to the database, it should be allocated directly to the database because there is only one wave number in the database. So now I can compute RRI and compare transmission loss. This is the transmission coefficient computed by RRI. Okay, and then Control G. This is the one we compute with analytical calculation, and we look at it. We see the ASEA result is the envelope of the actual result computed by RRI based on using all modes in of available up to 8 kilo, and you see that discrepancies observed when you have only 1, 2, 3 mode. But the correlation is quite good. And this is a total loss factor, total transmission loss, we observe that. In case of velocity, we can compare the RRI velocity to the analytical model. And we have to solve the analytical model, plot the velocity. and then Control G compared to the velocity, RRI velocity, and we see the match is much better because the velocity is only, the difference in terms of velocity with analytical is only proportional to sigma, while for transmission is proportional to sigma square. Then the error is twice in dB, twice the error. The error in transmission loss is twice the error on velocity square. And so you have a much better fit with the structural velocity. And what is interesting is now what we'll do is to use RRI spectrum in the junction here to make our analytical model hybrid, an hybrid model where we put all the numerical data within the connection. The first things we can do is to add, if I want to add transmission loss, is to create non-resonant transmission loss to replace mass flow or to replace black energy. I have to disable aperture, here enable user-defined transmission, and here I have to find one spectrum, but it's not available till I get it from RRI. So I need to go back to RRI and export everything I need to RRI for hybridization first. Then first things I have to edit first is to compute RRI, edit the transmission loss, and send this transmission loss to the database with the header RRI in order I'm not mistaken. Dialog box is here. Okay, and then I need to export. So I need to export the radiation efficiency as well. And here I will export RRI radiation efficiency. Okay, now everything is available in the database, and I just have to use that in the model. So how to do it? I edit the connector, go to user define, the acoustic to structure connection, and simply use, for example, the RRI radiation efficiency average in the connection. All right. And after I need to create, I will disable the non-resonant energy. And replace it by a direct connection between the two cavities. So in that case, I will import a user-defined coefficient, transmission coefficient in the junction. So the junction is cavity to receiver, emitter cavity to receiver. That is the transmission loss, but in that case, it is reciprocal. And we use non-resonant transmission. So it's like a bit the mass law, but computed differently. And then we just put it here to show it's indirect coupling, and I can color it a little bit dark color. Control W to edit and change the color to something darker. I will use this color. Apply. All right, so now I have the resonant and the non-resonant transfer of energy. In that case, I can redo the TL. Well, the TL will be only valid up to 8 kilo, because above there's nothing that tells the software how to compute. In the ASEA analysis, analytical ASEA analysis, it's not like a virtual model. The user-defined stopped in the junction above it's when the value are not available. There is no way to tell it that it is a mass law, for example. Then I have to stop the calculation. Go to calculation to 8 kilo in order not to be, and even is 6 kilohertz because the band is not fully complete. 600. It's not fully complete. Up to the 8 kilohertz is not fully covered, I would say. So in that case, I can to run the transmission loss, for example, with this data. I computed some transmission. And now I'm comparing to the transmission we got. Transmission we got, I have to fit into the recording window. Right. The transmission loss we got in the database. Transmission loss, so I will take the total transmission loss. Okay, and Control G. Now I compare with what we compute. And you see it's pretty the same. Huh? So that means if you have an analytical model or virtual ASEA, it works the same. It's perhaps better in a virtual ASEA model because automatically radiation efficiency can be expanded above the frequency limit because he has a model. But not for non-resonant mass. Huh? In that case, this has no type, the transmission loss. It's just a transmission loss you import between two cavities. There is no definition of what it is. Then you see that when you import the transmission loss within the virtual or the analytical model, it gives to this the same result than RRI, confirming that in fact RRI coefficients are the right coefficient to compute the transmission loss. And then you can give to any analytical model or virtual model the quality of computation. Because here it's a simple plate, obviously the analytical calculation is really correct, but you have noticed that there are still differences when you are in the domain of sparse modal distribution. Obviously, when you have a very complicated structure with ribs and curvature and so on, so you have to use RRI to get the right non-resonant energy transmission and the right resonant transmission in the low and mid frequency domain. And now we close it, this session. So in C+ implementation, we need then for computing this radiation efficiency from mode, first calculate the mode shape, all mode shape, amplitude over the surface we can analyze. And for this, we export then, we compute then the real mode, Nastran mode from finite element model. And then we export the model amplitude in an OP2 or PCH file. OP2 is binary, so smaller file, and PCH is text file. A little bit larger in general, 10 times or more than the binary file. Importing this file from ASEA database, that is how we do in C+. And then we will process the radiation, reciprocal integral radiation efficiency mapping from this file. And at the end, what we are storing is a 2D table of radiation efficiency per mode and per frequency. And this is stored in the database and an object that can be copied and passed through different projects. Post-processing of a given damping spectrum and user-defined band from the RRI can be performed, and we get different descriptors such as the total TL, the resonant and the non-resonant one. As well, V square total mean including the non-resonant velocity, and the resonant only, that mean only mode in the band are taken into account. And of course, modal radiation efficiency used by ASEA junction, that means the radiation of each mode at the resonance of frequency, which is a bit different from the mean radiation efficiency computed from the RRI table. And of course, the mass and also the local modal density due to the series of mode we use for this specific area. Only useful if we analyze the full structure.